Many real-world items are not pickable with conventional grippers due to their shape, size, or weight. In this paper, we address the challenging task of in-the-wild robotic picking as motivated by the grocery shopping task. Given the target item, the robot must drive to the item and retrieve it from the cluttered shelf. Through non-prehensile decluttering and bimanual grasping, our robot completed the task in both the replica store and a real-world grocery store. We built our pipeline around the TTT robot platform and uses driving and perception systems. We first plan bimanual grasps and their corresponding decluttering plan in case of occlusion. We rank and identify the most promising declutter grasp plans. If there is no occlusion, we execute the grasp. Otherwise, we declutter with non-prehensile nudging and restart with a new observation. We plan grasps in 2D to mitigate the impact of occlusions in the cluttered shelf. First, we fit an alpha shape to the item and sample potential grasp points along the contour. Unlike suction and parallel jaw gripper grasps, force closure and friction cone are non-trivial in a bimanual grasp. Thus, we formulate a maximum grasp planning optimization to find the grasp points that can robustly reject disturbances with the least grasp force. We then plan a decluttering strategy for each pair of grasp points in case they are occluded. We compute the minimum item movement required to pack the grippers next to the grasp points with an optimization. Sometimes only a subset of the candidate grasp points are occluded and requires decluttering. Thus, we jointly rank the decluttered grasp plans and select the most promising one. If decluttering is not needed, we perform a bimanual grasp with wrist force feedback. Otherwise, we declutter with nudging, which is a parameterized sequence of inserting the gripper, non-prehensile pushing, and withdrawing the gripper. After nudging, we restart the pipeline from visual observation until the item is grasped. We tested our method extensively using items challenging to suction cups and parallel jaw grippers. In the replica store, we achieved 90% pick success when there is no occlusion. In randomly generated clutter scenes, we achieved 67% success rate. Notably, when we ablate away decluttering and grasp directly in clutter, the success rate drops to 33%. This demonstrates the effectiveness of our method in overcoming end effector limitations for picking and clutter. We directly deployed our pipeline for testing in the real-world grocery store with no modification, and successfully picked new items in novel scenes. This further shows the robustness and wide applicability of our approach. Our method most frequently fails on extreme shelf heights and narrow items for two reasons. The first is kinematics. The robot may fail to reach the desired pose. For narrow items, the wrist link may come too close to collision and fail to apply the desired grasp force. This destabilizes the grasp. The second reason is camera perspective. The robot can only see the front of the item on tall shelves, which degrades segmentation and leads to incorrect pick plans.